All right, let's take a look at today's lesson. So today we are looking at two different things. We're looking at concavity and we're looking at the second derivative test for local extrema. Now both of these concepts really do have to do with the second derivative. They're just different concepts. So let's kind of jump into concavity first. So just, you may remember, you may not remember, you may be like, what are you talking about? So the shape of a curve that's concave down would look like this, right? It would be like curved down. This would be like concave down. Okay, so that would be like concave down. Concave up would be like curved, up. This would be an example of concave up. That's just what it would physically look like on a graph. If you had to read it off of a graph, you would look for the curve, and if it's curved down, that would be concave down, and if it was curved up, that would be concave up. So I hope that really makes sense why I made a note down here, because this is sometimes confusing. Straight lines have no concavity. There's no concavity of a straight line because there's no curve in it. There's no curvature. It's just straight. So straight lines don't have any concavity. So that's the concept, concave up, concave down, that we're looking at. There are two ways to determine whether a function is concave up or concave down. So these are the two different ways, and let's kind of focus on these for just a moment. So the first way is the definition of concavity. And so what this way does is it says the graph is concave up if the first derivative is increasing on the interval. Okay, so this is the definition, and that can kind of be confusing to students. They're like, concave up? Okay, so yes. The concavity, we like to use the second derivative, but sometimes we can't. We have to use the first derivative. And if that is the case, we use the definition. So let's just make ourselves a note right here. We use this if we have a graph of f prime or only have access to f prime. Okay, that's when we use the definition. We use it if we have a graph of f prime. We have to use this if we have a graph of f prime. What I'm talking about by using it, I mean we use it as justification and figuring out how things are working. So we use this if we have a graph of f prime or we only have access. We only have access to f prime. Otherwise, we would prefer to use the second derivative. I'm just gonna be honest with you. We would prefer to use the second derivative. Sometimes we can't. So in the event that we can't use the second derivative, we look at what the first derivative is, if it's increasing or decreasing. So the function f is concave up if f prime is increasing. For concave down, f is concave down if f prime is decreasing. So those are two concepts we need to link together in our minds. Concave down, f prime decreasing, concave up, f prime increasing. Okay, so that's using the first derivative. The way that I prefer actually to do concavity is to use the second derivative. It's really, to be honest, the easiest. So I'm just going to circle this. This is really what I would prefer to use, is the second derivative. But we can't always do that. It's not always possible. Okay? Yes, we want the second derivative, right? That's what we want. Okay. So first of all, of course, to get the second derivative, the function has to be twice differentiable. Okay. To have the second derivative, the function has to be twice differentiable. Now, if the second derivative is positive, then f is concave up. So if the second derivative is positive, f is concave up. I kind of like that. That's cleaner and easier, right? It's kind of like increase, decrease. Remember when we did that? If f prime is positive, f is increasing. Now, if f double prime is positive, f is concave up. They kind of match each other. They kind of go together, I think. If f double prime is negative, Okay, if F double prime is negative, then F is concave down. Again, kind of trying to tie it to something we already know. If you remember, if F prime is negative, F is decreasing. If F double prime is negative, F is concave down. That kind of hopefully helps put those things together. So those are the two different tests that we use for concavity. And for this one, for test for concavity, we would, I'll make a little note. Okay, so we use this one if we have a graph of F double prime, if we have a graph of F double prime, or access to the equation for F double prime. That's when we would use this one. Okay, so I think it's important for you to understand which one we use in what circumstance so that that's not confusing for you. That's what we do. Okay, so we use the definition if we have a graph of F prime or access to F prime's equation. We use test for concavity if we have a graph of F double prime or access to the equation for F double prime. All right, any questions on how to determine concavity? Okay. So let's look at the one other thing to do with concavity, and that's called point of inflection. A point of inflection is specifically where the concavity changes. Where the concavity changes is the point of inflection, and they will ask us to find those. So how do we determine if the concavity changes? What tests do we use? Let's just write ourselves a note. So if F prime goes from increase to decrease or decrease to increase, we have a point of inflection. That's from the first time, like we're using the definition of concavity. If F prime goes from increase to decrease or decrease to increase, then we have a point of inflection. Well, what if we have the second derivative? If we have the second derivative, if F double prime changes signs. Both of these are ways to determine, and the only ways to determine if you have a point of inflection. So you're going to need to either use the first way or the second way. Okay, so we either look at F prime going from increase to decrease or decrease to increase, or if F double prime changes signs. All right, so how are we doing on concavity and points of inflection? Okay, so let's talk about then the second topic for today, which is the second derivative test for local extrema. So first of all, I want to remind you about the first derivative test for local extrema. We got that right back here. I just want to remind you, we're going to go through it for just a moment. Okay, and remember why I told you have to memorize it? You were so excited about that? Yes, so this was the first derivative test. Let's talk about it. So the first derivative test, local extrema is relative max, relative min. The test was if F prime changes from negative to positive, we have a local min. If F prime changes from positive to negative, we have a local max. And if F prime does not change signs, there's no local extrema. Okay, that's what we learned last time. Let's look to see how the second derivative test for local extrema is different. Okay, that's what we're working on today. It's still about local extrema, but this is the second derivative test. So what do we need for the second derivative test? And guess what? You get to memorize this one too. I know, this is so great. It's another 3. So we need F double prime to be continuous. Okay, well that makes sense. These are the parts right here. F prime has to be 0. So these are our qualifications. In all 3 circumstances, F prime has to be 0. At C, which would be like a critical number. You know, this is at X equals C, right? So F prime is 0. So now let's see what happens. If F prime is 0 and F double prime is negative, then we have a local maximum. Now, that might seem counterintuitive. F prime is negative, but we have a maximum. Let's think back to what we just learned about concavity. What does F double prime being negative tell us about concavity? Which one is that? Is that concave up or concave down? F double prime being negative. That's concave down. So if I have a concave down and I have a local extrema, it would totally make sense, that that location is going to be a maximum, right? That would make sense. Okay, let's look at the second option. If the first derivative is 0 and F double prime is positive, then we have a local minimum. Now, why is that? So positive is minimum? That makes no sense. Unless you think about what does it mean for F double prime to be positive? Which kind of concavity is that? That's concave up. So if I have a function that's concave up and I've got that critical number, well, of course it's going to be a minimum. Now, I hesitate to talk, I'm just going to be honest with you, I hesitate to talk about concavity when I'm talking about the second derivative test, because what I've found students do sometimes is instead of using it to talk about extrema, local extrema, they use it to talk about concavity. It's not about concavity. I'm just explaining to you why. Why is it that those work that way? Why? Not that we would use concavity. The third option is if the first derivative is 0 and the second derivative is 0, then it's kind of a sad day. The test fails. We don't know. We don't know what's happening. The test fails. We do not know. We don't know if there's a relative max, relative min, or there's nothing there. We just don't know. So basically the test fails, and which is one of the reasons this is not my go-to test, because it can fail. It can fail. Now, sometimes they can force us to use this test because they love this test, but sometimes it fails. So I'm just throwing that out there. So those are the two concepts we're going to be working on today. That's the overview, or the conceptual view. Are we okay with that? Okay, so let's work some examples to kind of dig in and see what in the world I was just talking about. So finding intervals of concavity. I can either use the definition or the test. The definition would make me figure out whether f prime is increasing and decreasing, and I really don't want to do that with an equation. I would much prefer to look at the second derivative sign to determine what's going on. So that's what I'm going to do. Okay, it's not that I can't use the first one, it's just the second one would be easier. So here we go. Let's take the first derivative. The first derivative, I do my power rule. I bring the 4 down. I get x cubed. Bring the 2 down, negative 12x. The derivative of x is 1. Now, if I wanted to figure out increase, decrease for first derivative, I would stop here and do a sign chart and try to figure all that out. I want to actually go to the second derivative. Okay, so I'm going to do the second derivative. So the derivative of x cubed is, what, 3x squared. The derivative of negative 12x is negative 12. Then what we're going to do is, much like with the increase-decrease test, we're going to set the second derivative equal to 0, and we're going to see what our numbers would be. Where would the second derivative be 0? Because that's part of the requirement. If you look up here, the requirement is for the first derivative to be 0. That's the requirement to use this test. The first derivative has to be 0. And over here, test for concavity, we're looking for the sign of f prime, the sign of it. So if you want the sign of it, we're going to have to set it equal to 0 and do a sign chart. Okay, so that's what we're going to do. We're going to do a sign chart. We're looking for intervals of concavity. So, I don't know, I think I want to factor out a 3. And then I solve. I have, divide the 3 off. I have what? X plus 2, x minus 2. So I've got x is plus or minus 2. Okay, we're going to do our sign chart. We did some the other day. Hopefully they're comfortable for you. So here's what is important. Where do I plug in? Remember, I've got to pick sample numbers from each of these sections to test. What equation do I go to test them in? I go to the equation I got the numbers from. Where did I get these numbers from? I got them from the second derivative, so that's the one I'm going to put the numbers back, the testing numbers in. Okay, so I put in a -3. You can either put it here in the factored part or here. It doesn't matter. You put in a -3, you check the signs, it's going to come out positive. You put in a 0, that's like my favorite one to put in, 0, and I get a negative. Put in like a 3, and I get a positive. All right, so we're going to write down our intervals concavity according to the sign chart. We're going to say we're concave up from -infinity to -2 and 2 to infinity. Always say why, because f double prime is greater than 0. Okay, we're using our test for concavity. We're using the second one. We're concave down from -2 to 2 because f double prime is less than 0. And that is our answer to the intervals of concavity. So our very first example on concavity, how are we doing? We okay? Sure. Okay, so that was using a function, finding the second derivative, using the test for concavity. This is my favorite one. All right, now let's investigate different situations where we really don't have a choice. On this first one, we really had a choice. I could have done either one. But on number 2, I don't really have a choice. Look what I'm given. I'm given the graph of f prime. Okay, this is the graph of f prime. I'm going to make a big deal out of it. I'm going to circle it. I don't know what you need to do, like make sparkles. I don't know. You've got to realize it's the first derivative graph, because if you don't, it's very possible you could interpret it incorrectly. In fact, you will interpret it incorrectly unless you realize it's the first derivative graph. So here's what I like to do. I like sign charts. I just do. This was a sign chart for the second derivative. That's what that sign chart was for. Okay, this was a second derivative sign chart. I want to do a sign chart for this graph because I don't really want to like interpret the graph over and over again. I want to do a sign chart and then just look on the sign chart. That's what I want to do. So that's what we're going to do. All right, so let's do that. So what do? I like to draw the number line right there. Now, we need to think about this. Now, how do I read the second derivative off of a first derivative graph? What am I looking for? I'm looking for slopes. That's what I'm looking for. I'm looking for slopes. So my critical numbers would be where the slopes change. Where the slopes change. So at -1, at 1, and at 2. So here, and this one stops right here. It doesn't go past -4. So here, the slopes are negative. Okay, here the slopes are positive. Here the slope is negative. And here the slope is positive. Question? Are we good? So I'm just interpreting off the graph. Now this is a sign chart for the second derivative. So what am I going to do? I'm going to do everything they've said. Points of inflection, we'll do concavity first because that's what we've done already. So we're going to say we're concave up from -1 to 1. I'm just looking on my sign chart and seeing which sections are positive. And from 2 to 3. Now I have a picture of f prime. What justification do I have to use? Yeah, I have to do this step one here, right here. I have to say because f prime is increasing or f prime is decreasing. I have to use the definition. I don't have a choice. Okay, this is a type that I don't have a choice here. So why are we saying we're concave up? Because f prime is decreasing. Oops, we're concave up. So def prime, we're going up, is increasing. And you can see on the chart, on our table, why that makes sense. So we know the second derivative is positive because the slopes are positive, and we also know that the first derivative is increasing. So maybe that makes a little bit more sense why that works, for the first derivative to be increasing. We are concave down from -4 to -1 and 1 to 2 because f prime is decreasing. Okay? So I'm just going to remind you the reason we had to use this was because we have an f prime graph, which is what I told you right up here. You have to use this one if you have an f prime graph. Okay? And for concavity, you're going to have to use this one. For inflection points, you're going to have to use this one if you have an f prime graph. I'm really trying to separate it out and make it as easy as possible. I'm telling you exactly what you need. Okay, exactly. So we're going to say we have points of inflection at x equals, let's see, where do we change at -1, at 1, and at 2, because f prime changes from, and you can abbreviate like I am, increase to decrease or decrease to increase. And there's our answer for the graph of f prime. So I want to pause there for a second and make sure we're okay. Okay, so we just had an f prime graph. I did a sign chart for f double prime on it because that makes me happy. It's easier to look at the second derivative. We determined where we're concave up, concave down, justified, and points of inflection. Question on the first derivative graph.
What does the CHGFR stand for?
Change from. Yeah, and you can write that word out. I guess I'm being lazy. You can just say change from. I'll just write it up there. So we'll say it changed from. Okay. We good with the first derivative graph? Okay, let's look at the second derivative. Now we have a second derivative graph. Oh goodness, what are we going to do here? Well, I still want to do a sign chart. I'm still going to do a sign chart. Those help me so much. I'm going to write the sign chart right on top of the graph. Now, I'm wanting to know the signs of f double prime, and I have a picture of f double prime. What am I looking for the signs? On this first derivative graph, I was looking at slopes. What am I going to be looking at for the signs of f double prime on an f double prime graph? Like if it's above the x-axis or below, right? That's what I'm looking for. Is it above the x-axis or below the x-axis? That's how I'm going to determine the signs of f double prime. This is an f double prime sign chart. So I can see that at -3, it goes from positive to negative. Let's see how long it stays negative. It stays negative all the way to 1, so this section is negative. Let's see, so we're positive up here, and this section is positive, and then this section is negative. I hope you can see how terribly wrong your interpretations would be if you thought this was a first derivative graph. You with me? Really important, really important. Like, I don't know what you need to do, like circle it, make a note. I don't know. The interpretations are going to be completely different. And I will have to tell you, an unfortunate fact is I have had students on a test interpret the graph the exact opposite way. Like, I gave them a first derivative graph and they thought it was a position graph, or I gave them a second derivative graph and they thought it was a position, or all kinds of scenarios. What do you think happened? Were they able to get anything right? No, not hardly anything. So please, please be aware. You have to know which graph you're looking at and how to interpret the different graphs, okay? So here we go. Now we got a sign chart, which is what I'm going for, because sign charts, I can read sign charts. We're going, again, points of inflection and intervals of concavity. Okay, we got this. So here we go. So we are concave up from, and this is an arrow, right? So we're going to go from negative infinity to negative 3, and from 1 to 3, because I have a picture of f double prime. So now I can use that because f double prime is greater than 0. See, that's much easier to write. I like that way better. We're concave down. Concave down from negative 3 to 1 and from 3 to infinity because f double prime is less than 0. Very handy. Our inflection points are at x equals, let's see, where does the second derivative change sign? It changes sign at negative 3, at 1, and then at 3. And then we would say because f double prime changes signs. I think that's why I like this using the second derivative, is because it's just easier to write out than using the first derivative about concavity and stuff. All right, how we doing? We okay? Okay, we've got one more page of examples. So let's go to that. All right, number 4. Does the line tangent to the graph of, and they give us some equation at 1, lie above or below the graph y? Okay, so let's investigate that. So here, let's think about being concave down. Okay, so this is concave down. My tangent line, if I have a tangent line on this curve, it's going to have to be on top of it, right? There's no way to put it underneath it. So if the curve is concave down, then the tangent line, tangent line is above. Okay, you with me? That makes sense. If the curve is concave down, the tangent line is above. Let's look at the other scenario. What if at 1, that's what we're interested in, at 1, what if at 1 the curve is concave up? So this is concave up. What happens then? Okay, where would my tangent line be? Well, I hope you can see. If I could draw. Okay, that's close. I'm pretending that that's touching there. Okay, let's just pretend. Okay, my tangent line, if we look at this, my tangent line is below the curve, right? The tangent line is below.
Does it have to be on that side?
Nope, it could be on any side. I could have drawn it like over here. Oops. and the tangent line would still be below, and the tangent line would still be above. So it doesn't matter where it is on the curve, as long as it just matters about the concavity. All right, so how are we going to answer this question? Does the graph lie above or below the graph? Well, we're going to have to find out what the sign of f double prime. Whew, so that means we're going to have to find the first derivative, then the second derivative. Okay, I want you to look at this. Tell me, what derivative rule am I going to use to take that derivative? Product rule. I'm going to use the product rule, which is fg plus fg, first things first, second things second. Here we go. F prime of x equals. So the derivative of x is 1. Copy paste g, the e to the negative x is g, plus copy paste x. The derivative of e to the negative x is a chain, right? E to the negative x is a chain. The derivative of e to the box is e to the box times the derivative of the box. What is the derivative of negative x? Negative 1. And that is my first derivative. Now, I'm going to clean it up a little bit because I've got to take the second derivative. So let's just clean it up just a little bit. So this is e to the negative x minus x e to the negative x. Okay. So here we go. So I'm just going to, so that we know what we're doing, I'm just going to draw a line here so that we know that was first derivative work. Okay, just to separate our work. Now let's look at the second derivative. Now the derivative of e to the negative x, we just did that just a second ago. Pretty easy. It's just a chain rule, right? It's negative e to the negative x. That one's easy. Now when I do the product rule on this second thing, I'm going to treat this negative x as f and e to the negative x as g. That's what I'm going to do. You can do it differently if you want, but that's what I would prefer. So here we go. So the derivative of f, the derivative of negative x is negative 1, copy paste g, plus copy paste f. The derivative of e to the negative x, which we've already done twice before, is negative e to the negative x. Now this little guy we're going to have to work with, so let me clean this up so we can actually plug a 1 in. All right, so I've got negative e to the negative x. Let's see what's going on here. So this is a negative e to the negative x, this one right here. So what do we got here? We got a negative and a negative. That makes a positive. And then we've got x e to the negative x. All right, so now that ends our work for the second derivative.
Do you not combine like terms on the negative e to the negative x?
Yes, you totally can. You totally can. If I was going to stop here and just the second derivative was my answer, I would combine them. But since the purpose of this is to find out the value at 1, I'm not going to do that step. But you totally could. So f double prime of 1 would be negative e to the negative 1 minus e to the negative 1 plus 1 times e to the negative 1. Okay, so now see, I guess you combine terms now or later, right? We have to combine terms now. Maybe it would have been better to go ahead and do it. So I've got negative 1 e to the negative 1 minus 1, that's negative 2. E to the negative 1, I hope we know is that, right, is 1 over e. Plus, and that's, 1 over e. All right, so I can combine like terms, and I get, what, negative 1 over e. And that number is less than 0. Let's look at our little table, our little chart up here. If we're less than 0, if the first derivative is less than 0, are we concave up or concave down? What are we? Down. We're concave down. So that means the tangent line is above. So let's write out our answer. So therefore, I love the 3 little dots. The tangent line lies above F since F double prime is less than 0. And there's the answer they asked for. All right, how we doing? Okay. So, number 5, use the second derivative test to find the relative extrema. Oh, we need to change this wording. Is everybody done with number 4? Can I move on? Okay. We need to change the wording. This wording is not perfectly correct. So please add these words for me. Use the second derivative test to find the x values of relative extrema of that thing on this interval, and come back. Okay, that's nice. It just decided, it just wanted to stop. Okay. There we go. That was so weird. And classify. Okay, so we don't care about the y values because relative extrema, the extrema is all about the y values. We just care about the x values. All right, so we have to use a second derivative test, which means, yes, you got it. We're going to have to find the first and second derivative. Here we go. The first derivative, the derivative of the square root of 2 times x is the square root of 2. The derivative of negative 2 cosine would be, what, a positive 2 sine. And the second derivative test forces us to know where the first derivative is 0. So I'm going to go ahead and get that out of the way. 0 equals the square root of 2 plus 2 sine x. I know you're thinking, yay, we get to do some trig. That's what I'm thinking. So negative square root of 2, I'm solving. I want to divide by 2, so I get negative square root of 2 over 2 equals sine of x. Okay, let's do our unit circle. We know these are the 45, 45, 90s, right? That's what these are. And sine is negative, what, down here and down here. So I need to figure out what those angle measures are. Let's see, that'd be 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, that's 5 pi over 4, 6 pi over 4, and 7 pi over 4. Yes, I still have to count. Okay, so those are the 2 locations that we're interested in. Okay, so that's when f prime is 0. So what do we need to do? We need to find f double prime. So f double prime of x, let's see, the derivative of the square root of 2 is 0. The derivative of 2 sine is 2 cosine. Okay, so now let's do our tests. So we need to figure out f double prime of 5 pi over 4 is 2 cosine of 5 pi over 4. Let's see, what is that? Cosine of 5 pi over 4. Cosine is negative over here, so that would be what? Negative root 2 over 2. Okay, so that is less than 0. Okay, so let's do our other one. F double prime of 7 pi over 4. So that's 2 cosine of 7 pi over 4. Let's see, cosine over here is positive. So that's going to be 2 times root 2 over 2. And that's greater than 0. We have all of the information that we need to answer the question by using the second derivative test. Okay, so let's write our conclusion. So we're going to say we have a relative max at x equals 5 pi over 4 because, and you always have to say two reasons, because f prime of 5 pi over 4 is 0 and f double prime of 5 pi over 4 is less than 0. Okay. We have a relative min at x equals 7 pi over 4 because f prime of 7 pi over 4 is 0 and f double prime of 7 pi over 4 is greater than 0. Look at all these fun tests that you're learning today. This is so exciting. Okay. Now, of course, I have one really weird question. That's the last one. It's strange. I'm just going to be honest with you. It's weird. So that means it probably came from College Board, right? Probably. All right, let's look at it. Okay, here we go. Consider the differential equation that. So what's a differential equation? It's a derivative. I mean, that's all that means. That's fancy words for it's a derivative or has a derivative in it. One of those things. F of x is a particular solution to the differential equation with the initial condition of f of 0 equals 1. So what does this mean? This means that this is a position value. It's on the position. It's the position value. Okay, on the position, and the position is the solution. The solution is the position. Right, that's what a particular solution to a differential equation is. It's the position. And f of 0 is 1 is a position value. So we're just digging into the words right now. Does f have a relative minimum or relative maximum or neither at x equals 0? Justify. Okay. Well, I mean, they didn't even give us the position. That wasn't very nice of them, but they didn't. So I told you this one was weird. It is. So what do we need to do? Let's think about this point that they gave us. They certainly gave it to us for a reason. They didn't just give it to us for no reason. So if this is on, if that's on the position, so let's just pretend this is a position. I don't even know. All right, if that point is on the position, wouldn't it also be on the tangent line? Like, right, it would be there, because they're talking about x equals 0. They want to know about extrema. Wouldn't that value also be on the tangent line? It would, which means it's in the derivative. It's the same. So what are we going to do with that value? We're going to substitute it in here into this dy dx equation and see what happens. Okay, so I have dy dx at, and we're going to do it, I'm going to write it out at 0, 1 equals. Okay, so I have 1/2, I put a 0 in for x, plus I put a 1 in for y, minus 1. I go through that and I get 0. So what that just told me is that the first derivative is 0 there. That says it qualifies me to use the second derivative test. Okay, you with me? I'm qualified to use the second derivative test. So I need the second derivative. We have to take the second derivative implicitly. I know that's exciting. This is a mixture of x's and y's. They're being crazy with us here. But it's okay, we got this. So we're going to take the derivative of the derivative. So this would be the second derivative, d2y over dx2 is, so the derivative of, and with respect to x, it's with respect to x. So the derivative of 1/2 x with respect to x is 1/2. The derivative of y with respect to x is 1 dy dx. And the derivative of -1 is 0. Okay, that looks weird, doesn't it? That's weird. So what are we going to do with that? We're going to evaluate it at 0, 1. Okay. So the second derivative at 0, 1 is, so that's just a constant. What was the first derivative value at 0, 1?
0.
It was 0. Okay, so the second derivative is greater than 0. It's positive. So if the first derivative is 0 and the second derivative is positive, do we have a relative max or a relative min? We got a relative min. We got a relative min at x equals 0 because, and unfortunately we have to write this kind of notation, dx dy at 0, 1 is 0, and d2y over dx2 at 0, 1. And of course I put the 2 in the wrong place again. Who knows why? There we go. Is 1/2, which is greater than 0. And that's my justification.